Muy buenos días a todas y todos ustedes.
Good
Agradecemos
morning to
mucho.
all the people present here. We want to thank you for your presence here at this auditorium, and also we want to thank all the people watching us on social media. We want to thank Dr. Beatriz Ortega, director of the NCIT, as well as Dr. Peter Diaz, director of the Sciences and Technologie Institute. And especially we want to thank the support of the Coordination for Scientific Research through our coordinator, Dr. Soledad Funes. Thanks to all of them. Let's do a brief overview of this event and what has actually been all throughout these years. This event, the current panorama or overview of atmospheric sciences and climate change was launched initially in 2012 during the administration of Dr. Amparo Martinez. The idea was to bring outstanding people in the field of atmospheric sciences to this institute in the context of the 35th anniversary of the Center of Atmospheric Sciences, which was the name at the time. And it hasn't been easy to maintain this effort, but it has been going on or been taking place uninterruptedly for a total of 14 years, even during the pandemic. Another objective that we have achieved, an important one, is this. At the Atmospheric Sciences Center, which is today an institute, is that this institute is better known worldwide. We have distinguished guests all the time, but also we're talking about the fact that these individuals who are outstanding get to know our members and our experts, which was key in our transition from center to institute. So the idea, again, was to share current advances in the field of atmospheric sciences and climate change, as well as strengthening the development of atmospheric sciences in Mexico. And all throughout these 14 years, we have had the presence of researchers from 21 different countries, mainly from the US, of course, but among others, we have also had representatives from Europe, Spain, France, Portugal, Japan, etc. And also from distinguished universities like Harvard, University of Chicago, Sussex in the UK, Aveiro in Portugal, or Latin American universities, including Argentina, Bolivia, Brazil, Costa Rica, from which we have also had distinguished guests. We have not only had representatives of academia, but also from the operations sector. My point is this is an important area. We take care of monitoring of government institutions in our field. In particular, we had a visit from the National Center from Atmospheric Research, ENCA, the World Meteorological Association, as well as the Environmental Protection Agency from the US, and NOAA itself. How is the event organized? Well, we typically launch an invitation, which is launched by an organizing committee, which is formed every day, made up of our staff, representative of different departments, different genders and different subjects, with also staff with different areas of expertise in the institute and seniority. We promote the event through our available channels at the National University Radio, TV, our Gazette, and social media. It is always interesting to go over the evolution of our event, including the visit of distinguished guests. For example, in 2012, we had Dr. Thomas von Klarman. Let me move the slides. Sorry about that. This is the chart that shows the participation of different members of academia throughout the years and the presence of international institutions, as well as the process that takes place to launch and operate this event. We have a committee that invites the entire community of the Institute to propose guests with a series of criteria in terms of themes, budget, etc. And based on that, we come up with a proposal. And again, the second paragraph talks about our outreach activities. This was the call for participation in 2012, where we have Dr. Von Karman and Dr. Matilde Rusticucci, as well as staff from many institutions. At the time, we received 10 academicians who participated in the event over the course of 2 weeks. And then we also had another event with 2 weeks from many different countries in the world, including our dear Dr. Lawrence Mee, who with his vision, with his broad vision of not only of sciences, but the evolution of the planet, its environmental evolution, delivered a great speech. Or Dr. James O'Brien, both of them have passed away, unfortunately. All of these individuals you see here were present in our event in 2013. In 2014, we also have the presence mainly of people from the US, including Dr. Nicole Pirrone and Ryan Mates, and Dr. David Draymond, also highly renowned individual in the field of tropical cyclones, or Dr. Dennis Harman, who is the author of what is possibly the most widely used book on the theory of climate. Sorry. In 2015, we also had the presence of representatives from the US, including Dr. Gabriel Becky, who did the keynote speech. And also we had an important representation from people from other countries, mainly from the US. In 2016, we also have the participation of different academics, like Dr. David Guy, or, for example, Richard Rotuno from NCAR. I mean, we're talking about the highly renowned people worldwide in their different subjects. We also had the presence of representatives from the University of Bolivia, which is important because it's important to mention that we also have Latin American colleagues. In 2017. We had 10 talks with the presence of persons from Spain in different places, including the participation of Dr. Pedro Rivera from the Pablo de la Vida University in Seville. And in 2018, we also have 10 conferences, including one from Marie Delors from France, and we also had the presence of representatives from the UK, the US, etc. In 2019, we also had the presence of a diverse group of individuals, including outstanding universities like Harvard, Columbia, Arizona from the US, or the Aveiro University from Portugal, as well as the Arizona State University and the Costa Rica University. This was an important participation. In 2020, we only had 5 online lectures, all of them, again, online due to the pandemic. I mean, despite COVID-19, we maintained this academic event thanks to the efforts of the National University. And in 2021, since we were still amid the pandemic, we had the participation of academics from our own institute to present or share information about the work that was being done at the institute. And we also, that also allowed us to maintain this activity in 2020. In 2022, excuse me, we went back to a number of 10 lectures with a hybrid format with the presence of different institutions. In 2023, we reduced the number of lectures to 5 for budgetary reasons, but still maintaining the quality and the presence of different academics, including, well, I should say that all of them were outstanding, but you may remember the different academics presenting work. In 2024, we had 5 in-person lectures with people from different universities, including Texas A&M, with Dr. Steve DiMarco, and the University of California in Davis with Anthony Wexler, as well as the University of Trento with Simona Bordoni, who, thanks to this connection, organized an international event together with several academics from our institute that was held in Mexico. It was an international course organized by this institution, which on this occasion was held together with this institute. So this is the type of benefits that we have seen thanks to this event, and that was last year. But in previous events, we also had a series of benefits or positive actions as a result of this activity, this event. For this year, we have 5 lectures. First, we have Dr. Ottmar Möhler, who will talk to us today, Dr. Fabricio Villalobos Camacho on day 2. On day 3, Judith Show, who will be online, and then Lucia Caudillo Plat and Dr. Julio Sheinbaum. These lectures were hosted by Dr. Luis Ladino for the first talk, if you want to talk to these academics. For August 5, Julián Velasco, August 6, Dr. Elizabeth Vega, August 7, Oscar Peralta, and August 8, Rosario Romero. These are the different hosts for each of the different lectures. I also want to thank the organizing committee for this year, which is made up of Dr. Josefina Cortés Eslava, Master in Sciences, Dr. Bustamante and Carlos Alberto López Villalobos, as well as Dr. Augusto Peralta Rosales and Dr. Elizabeth Vega. They are part of the organizing committee, thanks to all of them. So this is in a nutshell the first information we wanted to share with you, and this opens our first series of lectures. And next, we want to ask Dr. Ladino to introduce our guest for today.
Hola a todos, muy buenas tardes.
Hi to everyone, good afternoon. It's a real pleasure for me and an honor for me to introduce the first speaker of this event, for our 2025
It's a real
event.
pleasure that you are here. Thank you for taking this such a long trip from Germany to Mexico and to share what you have been doing in the last decades and all your expertise. I'm pretty sure that our faculty colleagues and our students will appreciate it a lot. So next, I will introduce you in Spanish. Conozco al doctor Ottmar desde...
I've known Dr. Ottmar. Oh, first of all, Dr. Ottmar was part of my external jury when I got my PhD degree in Swiss. I faced a very critical committee, and after that, we began to interact as colleagues. Even though formally I was a student working in different projects, he's a researcher from the Technological Institute of Karlsruher since 1993, where he is currently the director of the AIDA project, which is one of the largest, if not the largest, chamber to do stratospheric and tropospheric research. He has published more than 170 scientific articles that reflects the impact he has had since he has joined the KIT with 12,000 quotes. He's been part of different committees and associations, including his participation in the International Commission on Clouds and Precipitation, the ICCP, International Committee on Nucleation and Atmospheric Aerosols, IDNA, the Committee of the North American Society of and the European Society for Aerosol Research. His scientific interests are focused on physics, ice-nucleation, lab studies on the interaction between aerosols and clouds, development and application of instruments for aerosols and ice-nucleating particles, as well as measurement of aerosols with remotely operated aircrafts.
Come here, and the floor is all yours. Thank you for coming.
Thank you so much, Luis. So I hope you can hear me well with the microphone. Everything is on, yeah? Okay, thanks so much, Luis. And I would like to thank the organizing committee and also you, Luis, for inviting me and having me here as a speaker in this event, which has such a long tradition, as the chairman just explained. And I saw in your list that already in the very first event in 2012, one of my colleagues seemed to be here from KIT. Yeah, so it's really a pleasure to be here and speak about my work and give you an overview of my work, not only with the PINE. I will explain what PINE is, also about my lab work with the facility, as was mentioned by Luis. It's not my first visit to Mexico, actually, but it's my first visit to Mexico Ciudad. So it's really a pleasure to be here and to talk to every one of you and to spend some days here in this nice environment and institute. Well, before I start, I would like to acknowledge contributions from my research team at KIT. So in particular, the ones highlighted in blue. And actually, the first two PhD students, Alexander Böhmland and Yatchong, who just graduated successfully last Friday before I came to here. So that was also a very nice success for my team, so to say. And I also would like to acknowledge my funding sources, which is mostly our Helmholtz Association, giving us the big money for research in Germany, also to other centers with which we collaborate in an atmospheric research program. And we receive funding from the German Science Foundation and also from our ministries and the European Union. So just to explain again where I'm from. So this is my hometown in Karlsruhe, Germany, with a long way to Mexico here. And so my home institution is Karlsruher Institute of Technology. This is a merger of a big research center and a university, actually, the first in its way in Germany, with a number of more than 9,000 employees and more than 25 or 24,000 students. And our institute has 4 parts. So I'm from the Institute of Meteorology and Climate Research, Atmospheric Aerosol Research. And the other ones, 2 of them are also located in Karlsruhe, and one so this is just a map of Europe, and we are here in Karlsruhe, the Rhine Valley, close to the French border, and our other 4th institute is located close to the German Alps in southern parts of Germany. Just to give you an idea where I come from and what is my home institution about. Okay, so this is the outline of my talk. I will have to talk about, or my major part is ice-nucleation. Ice-nucleation is related to aerosols, so I will give you a little bit of an introduction to aerosols and to the question why a minor fraction of those are important as ice-nucleating particles and why that is important for cloud and precipitation development. And then I give you a little bit of an insight into our developments in the laboratory and in the field in terms of methods and facilities, and also in particular ice-nucleating particle measurement methods, and give you a few research highlights at the end, as much as time allows in this hour. So I guess most of you may know, all of you, that aerosols have different types of sources. It's a variety of a mix of different types of particles in the atmosphere that originate from natural or also biogenic sources, but also anthropogenic sources, which are emitted and dispersed into the atmosphere. But there's also secondary aerosol formation. I think the fourth talk in this colloquium may target that a bit more. So the secondary particle formation based on chemical processes in the atmosphere. Many species are involved, organic and inorganic ones, which leads to the nucleation of new particles and to the formation of secondary aerosol components, for instance, which may also modify the emitted or dispersed particles in a way by chemical condensation or chemical processing. And all these particles then have major impacts on the climate system directly by scattering and absorbing radiation from the sun, and also indirectly by forming clouds or contributing to cloud formation and influencing cloud properties, also radiative properties of clouds, and by that also have a strong impact on the radiative transfer through the atmosphere and the climate system, mostly cooling, but with big uncertainties. And because of these big and major uncertainties, we want to learn more about the distribution, the dispersion, and the impact of all these aerosols in cloud formation, what we call aerosol cloud processes. And that is also our major concern in our work in the laboratory and in the field, to understand better where these ice-nucleating particles come from, how they impact cloud and precipitation formation, and how they are dispersed and do vary or are kind of influenced in the atmospheric system. So I would like to get into my method work, so to say. This is related to expansion type cloud simulation chambers. So I have to tell you also a little bit about stratospheric aerosols, and I tell you in a minute why I did that. So this is just an introduction to stratospheric aerosol. So now we have this kind of tropospheric air layer. I just mentioned the processes and dispersion of aerosols there. Now we are in the stratosphere, the layer above the troposphere, with altitudes between 10 to 50 kilometers typically. And the major source of aerosols there is a chemical coming from the oceans, which is OCS. So this is not chemically converted in troposphere, it's transported into the stratosphere, and only by radiation, UV, stronger UV radiation and OH radicals converted into sulfuric acid and nucleating new particles with water called Junge or stratospheric aerosol layer. Those are sulfuric acid water particles. And they eventually also then are fed by volcanic eruptions. So we're here in a volcanic environment, so big explosive volcanoes, as I'm sure all of you know, transport a lot of, episodically at least, SO2 into the stratosphere, and in contributing to an enhancement of that stratospheric aerosol layer, also contributing to sulfate or sulfuric acid aerosol formation. And eventually those particles coming into polar vortex also contribute to polar stratospheric cloud formation here and impacting the ozone layer, which is protecting us from harmful UV radiation. So this is the connection, so to say, from ocean emissions to the stratospheric aerosol layer to these aerosol clouds. And there's also maybe impact from meteor smoke. I'm not sure if you are interested in meteor or meteor showers. I think there is a Perseid shower in August coming along with a maximum in night of 12th, 13th August. If you're interested to see, in Germany at least, it was broadcasted that we get at least one meteor per minute during midnight time. It's a bit disadvantage that we have full moon at the time, so we may not see the weakest meteors, but you can watch for that if you're interested. So those are also impacting by ablating materials from interstellar space or interplanetary space into the mesopause region, transported down into small particles, nano-sized particles that could eventually also contribute to the nucleation, facilitate nucleation of new particles in the stratosphere, and eventually also some phase transformation in polar stratospheric clouds. That is not really my topic today, but I thought I can really touch on that a little bit, because there's also more recently detected that fire plume aerosol is also observed by LiDAR observations in the lowermost stratosphere and may also be transported upward and contribute to all these cloud processes. And I did tell you that because all these kind of stratospheric aerosols, that was discovered by a person called Christian Junge. He was, as a young postdoc, working in the United States and developed a balloon-borne instrument to measure aerosol particles in the troposphere and in the stratosphere. I think that was a bit of also a push to atmospheric aerosol research with this discovery, in particular in the stratosphere. He later became director of Max Planck Institute in Mainz. And I happened to hear a speech during a ceremony from him when I was a young scientist. That had a lot of inspiration to me to hear such a famous person with such a famous discovery in an evening speech. So he discovered that, and he used an expansion type instrument, a CC, a cloud condensation counter, sampling aerosol in a little volume of 10 cubic centimeters or so, having a light here, a flash lamp. And once in a while, when that chamber was filled with aerosols, he had a moving piston. He would expand that, condense water on the particles, and the tiny little particles initiate a flash lamp and illuminating the particles, the droplets, the little droplets that were formed by expansion in that volume. And then with just a simple optics, the scattered light was imaged on a photographic film moving around during the balloon flight. And in the lab, he was just counting out these lines of little dots. And by that, with the calibration in the lab, did get a number concentration of aerosol particles. And that was the first really high profile of aerosol particles in the atmosphere, which you can see here. So this is a temperature profile of 2 balloon flights or of 1 balloon flight. And this is the height spectrum of aerosol number concentrations. You can hardly read that, but this is 100, this is 10. So you see how the number concentrations are dropping off around the tropopause layer when the temperature has its minimum. So to say, and in the stratosphere, he did measure this concentration of particles still, and that's called the Junge aerosol layer. Those are these tiny little sulfuric acid water particles, which are still so important in our climate system and for these kind of stratospheric aerosol and polar stratospheric cloud processes. And actually, I told you that because I was inspired by this instrument and some other activities, also my big cloud chamber work to build this mobile instrument called PIME. It's basically a similar principle with expansion, but what we did here in this instrument is just we cool the walls. We do the same as Junge did to measure stratospheric aerosol at temperatures below 0 to not only measure aerosols, but also ice-nucleating particles. And I will explain in a minute how that really works in our instrument. Okay. I didn't check the time when I started to talk, but I think I'm good in time still. Okay, yeah, so this is that instrument. I'll come back to that in a minute, as I said. Well, the next chapter, role of aerosols in cloud formation, just to give a little bit of introduction to what we measure, ice-nucleating particles. So when we talk about cloud microphysics, so meteorologists like to sort out the cloud systems by their kind of shape or form or layer height, so stratiform, stratocumulus, and all these kind of names for methodology which are known. When we are interested in the cloud microphysics, so sometimes we call it also the secret life of clouds, what happens really inside a cloud? We are more concerned about the temperature these clouds exist. And then we have to look at the temperature profile in the atmosphere to know in which temperature regimes the clouds are formed and are developed. And then we can look at this mean temperature profile throughout the atmosphere from the surface all the way up to the mesopause region in 100 kilometers above surface. So we have the temperature decrease in the troposphere and then the increase in the stratosphere and decrease again in the mesosphere. And not everywhere, but in many places, of course, in the troposphere, we have these cloud formation processes going, but also in the stratosphere, as I already mentioned, we have the polar stratospheric clouds. And even in the mesopause, in the summer mesopause region, which is the coldest region in the Earth's atmosphere, so to say, with temperatures all the way down to minus 150 or so, minus 160 degrees centigrade. Ice clouds also form, and they may form by condensing or condensation, nucleation of water vapor on these meteor smoke particles, for instance, where they are ablating from the dust particles coming from interplanetary space. Okay, but in the troposphere, we have starting from warm clouds. So we distinguish between warm cloud, mixed phase cloud, and ice clouds. And so we have the warm clouds lower in the boundary layer in the lower troposphere. And then we have this regime or region of temperatures between 0 and minus 40 degrees centigrade, which is so important also for precipitation formation processes, because there the cloud can exist of both supercooled liquid water droplets and ice crystals. And there the ice-nucleating particles come into play to initiate a phase transition from liquid to ice in the clouds. And only at lower temperatures, all the clouds or particles, condensed particles, are in the form of ice only, or ice crystals, which is then in the cirrus regime, cirrus cloud regime. So I will go through that a little bit in the next schemes. And our concern is to understand the processes of ice formation in all these kind of tropospheric clouds, more at the moment, more in mixed phase and ice clouds with labs studies, lab facilities, and also with field work, including research aircraft. At the very end, I may introduce you to a little instrument we developed for research aircraft use now, just in the last few years. Okay, so the major role of aerosol in cloud formation is twofold, and I guess you know that. So this is just acting as cloud condensation nuclei and as ice-nucleating particles. And for the cloud condensation process, so this is because when air is, for instance, rising, is cooling, you need a surface for the water to condense on, so to say, because water alone, just from the gas phase, nucleation to the condensed phase would not happen in the atmosphere because supersaturations are never high enough to make this process happen. So nucleation of pure water vapor at room temperature into the liquid water would require a saturation ratio of about 5. And in the atmosphere, we have not reached that because aerosol particles are always there. And when you cool an air parcel with aerosol particles in them, the particles themselves are cool as well. So they provide cold surfaces, so to say. Simply speaking, of course, the process is a bit more complex with kernel theory and all that. But simply speaking, it's just cold surfaces where the water can condense on, and then the cloud droplets form and limit the supersaturation in the clouds to a value of only a few percent above saturation point. And many aerosol, the majority of aerosol can contribute to that process. This is not my topic today. So my topic is ice nucleation, and ice nucleation processes are even more, I would say, not just complicated, but maybe multifold. So we have different ways for ice to form in the atmosphere on particles or also without particles, which I go through in a minute a little bit. But to that process, only a very minor fraction of all the particles contribute. Let's say 1 in 1,000 particles or 1 in 1,000,000 particles, depending on temperature also and the type of particles. So this ice-nucleating process is a very selective process, which involves only a minor fraction of particles. And that's it so difficult also to understand which particles contribute, where they come from, and how they are modified during transport in the atmosphere, for instance. And this is what we are mostly interested in, to understand this formation of ice in the clouds or cirrus clouds or mixed phase clouds, and to understand which minor fraction of the aerosol really contributes to that process of primary ice formation in clouds. And this happens, as I said, in different ways or modes of ice nucleation. And so this is just a schematic, like you can understand that like a phase diagram of water vapor and also a height scale. So this is the temperature scale here, low temperatures here, high temperatures here. So you can understand this is like near the surface. This is in the tropopause region with temperatures around 190 degrees centigrade. And this line is where the ice phase or water in the ice phase is saturated. And this is the supersaturated regime for the ice phase in water vapor content in the atmosphere. And along this solid line, the supercooled liquid water is saturated. And you see starting from the triple point of water, where this process starts, we can penetrate into an ice supersaturated regime before we reach the saturation point of supercooled liquid water. So that means that only along this line, low in the atmosphere, water can condense to particles and form supercooled cloud droplets. They can only freeze homogeneously without an ice-nucleating particle at a temperature close to 35 or between 35 and 40, minus 35 and minus 40 degrees centigrade. So this is what we call homogeneous freezing, contributing to the glaciation of deep convective clouds at an altitude of 8 kilometers. So this is a very important process to really push convection to high altitudes in the tropics, for instance, by releasing latent heat of condensation of water vapor and freezing then later on. So latent heat of freezing then for homogeneous process. But below that, at higher temperatures, ice can only be formed by the action of these ice-nucleating particles. So they are really important to make cloud droplets freeze, and only then they can develop large sizes, can grow in expanse of the supercooled liquid because the saturation above the ice is lower than above the supercooled liquid. So droplets evaporate and the ice is growing, falling, forming hail. Secondary processes come into play. Precipitation develops, comes down either as hail or as melted ice rain, so to say, or rain, liquid rain. So this is the key process of rain formation over the continents. And only higher up in cirrus clouds, so ice-nucleating particles are equally important because they then control the number of ice crystals of cirrus clouds and also the radiative properties of cirrus clouds in the climate system. And to show how important that is, so this is just two references to work. The one is from Field and Heinzfield from 2015. This is a satellite retrieval of cloud properties with radar and LiDAR, and it shows the fraction in color scale. So fraction blue means low fraction, red means high fraction of clouds or events of precipitation that stems from ice in the clouds or from melting snow. And you see over the continents, you see these red colors, high fractions, so to say, in particular over continents where we have a lot of crustal material, a lot of dust, a lot of ice-nucleating particles. Most of the precipitation develops through the ice phase, so it's initiated through the ice phase, according to these measurements. And then on the right side, you see a study from Möhler's team in Leeds, a modeling study on the radiative transfer shortwave flux calculation in a modeling study of a cloud system over the Southern Ocean, which was modeled one with a high content of ice-nucleating particles and with a low content of ice-nucleating particles. So look, this is not per cubic centimeter, this is per liter. So 4 per liter in the air or 0.006, 0.6 per cubic meter in the air of ice-nucleating particles as a model parameter assumption. And you see that how the cloud look different. So this is more bright, has more radiative transfer, more cooling, where these clouds with more ice-nucleating particles have less scattering, lower shortwave flux effect, so to say, on the climate system. So indeed, the abundance of IMP matters for the cloud properties in the climate system. So that's why we need to know that also to improve climate modeling, cloud modeling, weather modeling for future climate projections as well. And just at the edge of getting better ideas of parameterizations for using climate models and things like that. So this is a big challenge, so to say. But it's also very important to know more about these IMPs. Okay, and now speaking more about ice-nucleating particles themselves. So I'm moving on towards the topic, so to say. This is again this diagram I showed already, and today I'm speaking more about what we call immersion freezing ice-nucleating particles. Those are these particles which act both as condensation nuclei, so in this regime, close to the supercooled liquid water saturated line, where the supercooled cloud droplets form at temperatures between 0 and minus 35 degrees centigrade. So the same particle eventually acts as a cloud condensation particle, lower up in a convective process, and then the cloud develops, is further kind of lifted up, cooled down to lower temperatures, and at some temperatures, suddenly this condensation particle immersed in the droplet acts as an ice nucleus or ice-nucleating particle, make this droplet freeze, and this is what we call immersion freezing. So it's induced by a solid particle immersed in a supercooled liquid cloud droplet. That's why we call it immersion freezing. That's the process I'm now talking most about in the remainder of this presentation. So there is a number of studies now already about the abundance of ice-nucleating particles. Luis's team is also working on that. And when he was in Switzerland, he was involved in some of these studies and many others. And this is just a sketch which was done by Samin Kanchi in a nice monograph paper, so to say, in 2017. It's a busy graph, so sorry for that. I only want to refer you to two things. So the one is the temperature scale. So this is measurements of the number concentration of ice-nucleating particles as a function of the temperature with certain methods. I come back to the methods in a minute. And the number concentration scale is shown here in a log scale. And you see this is a wide range of temperatures, and it's a wide range of concentrations in that log scale. Starting from 0.1 or so per cubic meter to almost 10 per liter, per cubic centimeter here. So orders of magnitude, very much depending on temperature, but not only, also depending on the region where you measure. So this is the color scale that indicates to the type of aerosol which were abundant in the region where these measurements were performed in the world. So this is just shown in yellow, for instance, and orange. Those are the dust-dominated areas with high concentrations at low temperatures. Or green, for instance, where biological aerosols were prominent, had major sources in forest environments, for instance, where you see relatively high concentrations at high temperatures and things like that, or some marine coastal environments where the concentrations are lower. But this is just a compilation of a certain number of studies, not much kind of time resolved or kind of specifically knowing details about the aerosol, but I think it's a nice compilation showing what it's about ice-nucleating particles, and that's why it's important to look more to understand better the real concentrations and their variability in space and time in the world. But it's already, I think, a nice overview of studies and measurements. So now talking more about methods and mostly about those we have developed at our institute. So those methods I already mentioned in my introduction are based on expansion type cloud simulation chambers. So I have to talk about that a bit more now. So mostly I start with some information about our big AIDA facility. And I started to work with that one. So it's, you see the person here, so it's really 7 meter high and 4 meter wide chamber in a cold room, which we can cool down to minus 90 degrees centigrade, and we can do some cloud and aerosol studies in this rigid tank, so to say, in certain ways, and we call that AIDA-C, the classical cloud chamber, because we developed more meanwhile. So we have a dynamic cloud simulation chamber, which is a bit more smaller. I do not have the time to talk much about that, but if anyone is interested, while I'm staying here, I can give you more insight. What is different and for this system compared to that one, and why we call it a dynamic chamber. So I'm not talking too much about that one. We use it more for convective type of cloud studies in the laboratory. And the most recent developments were the development of the smallest and mobile portable Ice-Nucleation experiment. So this is about 84 cubic meter volume, this is 10 cubic meter volume, and this is 10 liter volume only. But they're all doing the same. They are sampling aerosol and making expansion to study cloud formation and ice formation. And the most recent development is Pioneer, which is the aircraft version of the Pine instrument I can show you at the very end of my presentation. Here you see some photographs. This is a view into the lower part of this big AIDA chamber in the cold room, so to say. And this is this dynamic cloud simulation chamber AIDA-D, which came into operation just 5 years ago or so. Okay, so this is our laboratory building in Karlsruher. And just a few parameters for the AIDA facility. I do not need to go through all those details, but I already mentioned the temperature range we can investigate or target for our experiments. It's like a well-mixed cloud parcel. It's not like a cloud you know from the sky with edges and nice shapes and things like that. It's just like a well-mixed parcel of a cloud, which you have a good control of in terms of the pressure, the temperature, the moisture content, the supersaturation by pumping and things like that. And it's equipped with a full range of gas, aerosol and cloud instrumentation, also in situ spectroscopy there. So we have really a very comprehensive instrumentation there, so that we are well prepared to do not only cloud studies, but also aerosol and race gas studies. Nowadays, we also have a light system with LEDs shining into the system, so we also can do photochemical studies, but this is, as I said, not the topic today. And it has a mixing fan down there, so that we really have well mixed as much as possible homogeneous conditions inside to control the processes. Then just a little bit of an introduction for these expansion type cloud simulation chambers from basic methodological equations. So what happens when we use these cloud simulation chambers and lower the pressure? So what we do basically, we simulate processes that occur in an air parcel that is ascending or rising in the atmosphere, like in convective clouds. So when that happens, when an air parcel is rising in the atmosphere, what happens first? Of course, the pressure is decreasing because of a barometric height formula. So we are faced with that. And this pressure change we can now simulate in our chambers just by pumping. So we need strong pumps and some pump control, so to say, or pressure rate change control. Then when we change the pressure, we have adiabatic processes going on. If there is no heat exchange, if you have a really adiabatic system like in the atmosphere, in the chamber, it's not really adiabatic, so we have faults, we may have temperature gradients, we may have heat flux, we may have changing internal energy. So it's not really adiabatic, but we still have some cooling by expansion, quasi-adiabatic cooling. When we have cooling, according to Clausius-Clapeyron equation, we get a change in supersaturation, a decrease of that. And by that, relative humidity is rising. So by that, we can control the rate of change or rise or increase of relative humidity here, just by all these processes and equations. And in the end, we are just doing the same as the natural cloud is doing. We have a process starting from undersaturated condition here in this phase state diagram of water vapor, just pumping, and then the lower pressure goes down. So the partial pressure is a little bit decreasing, but the temperature is also decreasing the saturation pressure is decreasing. So we hit that saturation point, and at that point, the cloud starts to form. And this is what we have control of in our simulation chambers, whether it's the big AIDA or the small pipe chamber. It's always the same process. Just to give you an idea what we really do when we do an expansion experiment. Okay? And this is an example of a time series of such an experiment in the big AIDA facility now, the AIDA chamber. So we start from almost constant pressure and temperature control. So this is a Kelvin scale. So this is about -20 degrees centigrade. We added some dust particles in this case. So we have an optical particle counter. Those are just the largest aerosol particles with their optical size in micrometers here. And we measure the relative humidity with in situ TDL spectroscopy. So this is an in situ spectroscopic technique that really measures the molecular water vapor partial pressure inside the chamber. From that, we then calculate with very accurate temperature measurements and the saturation equation, relative humidity with respect to ice phase and with respect to liquid phase, which is always lower than the one for ice, yeah? Because of the one is thermodynamically stable, the other not. So we are supercooled liquid. And then we start pumping at a certain point, time 0 here in seconds. So pressure goes down, temperature goes down. This would be the adiabatic behavior, but here we have warm walls, so we get a little bit of a deviation from the adiabatic profile here already, but we get increase of relative humidity. So here we are already well in the ice supersaturated regime, but nothing happened to the particles yet, to the aerosol particles. But here now the next step is that we exceed water saturation, and then suddenly we see the formation of a supercooled liquid cloud. Those are the cloud droplets measured with the optical particle counter in a narrow distribution. This is a typical narrow size distribution of a supercooled liquid droplet cloud that formed by condensation of water to dust particles acting as CCN at a temperature close to -25 degrees centigrade. So we really do CCN activation at low temperatures in that sense. And then we further cooled by further pumping. And with further cooling, suddenly a third class of particles, even larger ones, occurred to be detected with the OPC. And those are the ice crystals that were formed by immersion freezing of some of the droplets with a dust particle in it. Every droplet was grown on a dust particle here. So every droplet contains a dust particle. So that means we can then measure the number of ice that forms with time or with cooling in our experiment and quantify that. Okay, and then what we do in our analysis and parameterization of such studies, also in the interest of using that for modeling, is that we now relate that number of ice that forms with time to the number of ice that forms with cooling, with temperature change times the cooling rate. And we have a parametric kind of a parameter defined now that now describes the formation of ice upon cooling. And we call that ice nucleation active site density parameter. That's just the number of ice active sites in immersion mode on that particular dust type, so to say, as a function of the temperature per aerosol surface area concentration. So we relate the number of ice that forms when we cool to the surface area concentration of the aerosol that contributes to that ice formation. And that's what we call NS, or inner density parameterization. Then we can formulate the number of ice that forms with cooling as the rate of change of that NS parameter, just times the aerosol number concentration. And what we do in the lab, so we measure this one here in the lab, and also the number of ice that forms, and get a fit of this NS to our experimental result. And when you apply that in a model, and the model knows this thing for particular aerosol, like a dust aerosol, knows the number of the aerosol surface concentration in a certain parcel of the model. And then upon cooling, the model can then predict with this simple formula the number of ice that forms with temperature change, according to that parameter here. So this is the vice versa application of what we develop in the lab as parameterization for ice formation, so to say, upon temperature change. A very simple concept, so to say. And we did a number of experiments of that in our chambers. I'll show you an example in a minute. Just want to explain what's behind this NS, or inner density parameter, as an important parameter for our experimental studies and for the application in cloud and climate models. Okay, and then as I said, I would like to talk more about the pipe chamber. So in the pipe, we do basically the same. So I do not need to go through all the details. We fill this 10-liter chamber with a certain ambient aerosol in a measurement site, a mountain station or wherever. We fill it with the aerosol. We have a flush period. So this is the first mode. Then we do an expansion. We get the cloud droplets. We get the ice particles as well. And we then can just relate the number of ice we measure in such a run, in an expansion run, to the volume of the chamber where they formed in, and we get a number concentration of ice-nucleating particles. So this is what we do here. And then if we then just compare that to the AIDA data set, so it's fairly similar. So this is the 84 cubic meter experiment, and that's the 10-liter experiment. Just the time scale is shorter, and we have maybe a bit more problem with homogeneity and wall effects and all that, temperature accuracy and things like that. So of course here we have better measurement system, but here we can do fast evaluation and autonomous or automatic operation of these repeated cycles of flushing, sampling aerosol, expanding and refilling the chamber. And we do that in repeated way in an automated operation series with this Pine instrument. So this is a series of 5 or so repeated expansions. So every 6 minutes or so, we get an information about the number of ice that forms upon this kind of process. So we measure the number of ice-nucleating particles as a function of the temperature here in the system, which we measure also, and can then relate the number of ice we measure to the number of IMPs at a particular temperature. Can vary the temperature from the wall temperature control. So we that also get temperature spectra or the temperature-dependent measurements and things like that. So that's what we basically do with the Pine instrument in automatic 24/7 remote control operation, so to say. Okay, so how much time is left?
Very good.
I'm good. Okay. So that was the introduction and a little bit of an explanation of our methods, both for the AIDA chamber, the big chamber, and the small ones, this Pine instrument. And I just go through a little bit of results and research we did with these facilities and instruments. The first is an old example from the AIDA studies. So that was published already in the early 2012 and 2017 years. So that was a series of experiments of immersion freezing for desert dust, which we got from certain desert areas around the world, mostly the Saharan deserts and the Asian deserts. So you see the labels here for the different dust we investigated. So ST means Saharan desert. This one came from Israel, so Middle East dust. Those were the Asian desert samples. And what we did here, we just filled the chamber, we dispersed those samples, so we get just surface samples, a bottle of soil or sand from a desert area. We sieve it to particles smaller than typically 70 micrometer. Then we disperse that and pass it through a cyclone so that we only fill or disperse particles smaller than typically 5 micrometer in diameter into our chamber. And here you see a typical size distribution of what we measure as a dispersed aerosol from these dust samples into our facility in a big aerosol chamber. So this is 0.1 micrometer, 1 micrometer, 10 micrometer. So you see the peak in this case. So this is already the surface observation, which we need to calculate this inner density parameter. I try to explain to you what it means. So the peak is just close to 1 micrometer in this surface mode of size distribution. And then what we measure in the course of the time of these expansion experiments, I just gave you an example of a time series, we measure how the ice forms. So this is the number of ice crystals that were detected in the experiment. This is the number of droplets. And then we again relate the number of ice to the surface area concentration to calculate that NS parameter as the ratio of number of ice and surface area concentration of the aerosol all sitting in these cloud droplets. And then we did several experiments with all these samples from the different locations around the world and at different temperatures. So this is a temperature scale now, and those are the results. So the symbols showing you the NS parameters calculated from these experiments with the different samples colored here and at the different temperatures. And you see that they all follow a simple fit line. So that means that on average, with a certain range of variability within an order of magnitude or so, all these dust particles did behave in a similar way to induce ice formation immersion mode. So that means that whenever a model knows the surface area concentration, for instance, of these dust particles, whether they come from the Sahara or Asian deserts, you could apply that parameter line to predict the number of IMPs and the number of primary ice formation in a model process, for instance, or even predict maybe at a certain site of measurement to compare what you measure with what the model predicts with these laboratory-based result of a parameterization for ice nucleation activity, so to say. That's the interest of that. And this high ice nucleation, it's really high ice nucleation activity. You may not have a feeling for this unit per square meter of aerosol, but you know that it's steeply increasing with lower temperatures. So at, let's say -25 or so, we have a very large or high ice nucleation activity. And now I can give you an example of measurements with the PINE instrument at 2 locations in Europe. So that it happened that in 2022, when we had a severe Saharan dust storm coming along across Northern Europe, so we had 2 of these PINE instruments operated, the one in a station in Austria. So that's a Sonnenblick Observatory. That's a high altitude station, more than 3,000 meters above sea level, where one of our PINE measured, and the other one was in Greece at Mount Chelmos in Peloponnese, also a high altitude mountain station, receiving quite often or frequently desert dust from the Sahara. And you see when this is just the dust forecast model, and on the 22nd of March, when the dust cloud then finally arrived first at the Sonnenblick in Austria, we did see a steep increase. So this is the red color, I think, a steep increase in the ice-nucleating particle concentration related to the dust plume coming along. So with these fully automated and high time-resolved measurements, we can then relate what we measure in the change in INP concentration to such events and understand better their contribution and role in cloud formation processes. And then a day later or so this is just a webcam of the situation. It's really a natural color. It looked like that. So this is the dust cloud at the Sonnenblick station in the high mountain area at Sonnenblick in the Hohe environment south of Salzburg. And then a day later, that same cloud then finally propagated towards the southeast, towards Greece, and then we did see an increase of that instrument just a day later. This is also good to constrain modeling prediction of dust. Of course, you could also measure the aerosol, which is done in these stations anyway, but it's also nice to have a direct measure of the ice-nucleating particles, which we then can relate to the aerosol abundance and also to some methodological or modeling scenarios, so to say. I think it's a nice case study showing really this value of such an instrument to measure at high time resolution such kind of parameters here. It's an unpublished material that we still have to write up and publish that also together with all the modeling and the parameterization work for the dust itself. Okay, now I just move on with more examples of field measurements of ice-nucleating particles. And there's another method we are also using, and the team of Luis is also using. So this is so-called offline techniques. We call ours INSECT, or Ice Nucleation Spectrometer of the Karlsruher Institute of Technology. The one here is used UNAM droplet freezing assay. It's basically a similar principle. So what we do there, we collect aerosol particles on filters, and then in the lab, we wash off for a certain time. So this has to be done over at least hours or days, depending on the number concentration of aerosols and ice-nucleating particles we want to measure. Then we put that on such a rotating washing machine. So we wash off the particles from the filter into clean water and then distribute the suspensions of the particles in the water into wells of a PCR plate, put that in a cold stage and cool it down and measure how many of the wells with the particles and the IMPs in it freeze at a certain temperature. And by that, we get the number concentration of IMPs as a function of the temperature of the process where they act as ice-nucleating particles. So that's what we basically do. And so there was a first kind of intercomparison study with these kind of offline freezing techniques, which are used in a number of labs around the world. So this is the UNAM here, the blue rectangulars. So our INSECT is here in the blue triangles. And you see a time series of measurements at the Puy-de-Dôme station here. That was a campaign in, I think, 2018, where you also participated. I think I met you there also in person. And Paul de Motte was there also. That was really great to also be with Paul de Motte in the same campaign. And one of our prototype of PINE was there, and the INSECT method was applied together with some others. And you see the difficulties of these methods. They're really great of measuring IMPs at very high concentration. high sensitivity to very low number concentrations here and high temperatures. So those are time series measured over, I don't know, 2 weeks almost. Every data is from 1 day of sampling of aerosol from the different methods. For the same air sample with split inlets, some did measure rooftop sampling systems, others in the laboratory through a sampling line and an inlet line. And those are the results analyzed for -10, -15, and -20 degrees centigrade of activation temperature. And you see some similar behavior of the general trends, but there is still a wide range of variability, or could also say uncertainty of the measurements or disagreement. And we're still faced with that problem quite a lot. And this is one of the reasons why in Europe at the moment we are developing a better kind of operating procedures for these methods in the framework of a process or a project we call ACTRIS. So this is a pan-European distributed infrastructure we develop to also measure ice-nucleating particles. And my team has, or my colleague has the leadership. So Christina Möhler is leading that unit in my institute. So to provide services and information about how that should be applied, how we develop calibration measures, how we develop kind of quality assurance measures for applying these methods for long-term quality controlled measurement of ice-nucleating particles in different locations, which we then are able to better compare to each other, or are better comparable to each other. So there's a lot of activities going on at the moment, at least in Europe, in the context of this ACTRIS framework. Okay, so for the online, lucky enough, that was a bit better agreement, but also there we have issues. So there were 3 instruments which did sample the same aerosol also for with online analysis. So the one was the instrument from Ottmar from CSU, the other was the SPIN, which was marketed for some years by DMT, and the other was our prototype of the Pine. And this is just now a shorter record. We didn't have so many matching times where we could compare our data in this campaign. But this is one example where you see a very nice agreement. And I was very happy to see that, because that was really the prototype system of the Pine, very young still, that it was so well in agreement with, for instance, this established instrument from Ottmar. So that motivated me to go further in this direction, develop that instrument further for use in other locations as well. And here you see just a photo of the developing team. So Larissa Lach is still working in my team, and those are the engineers from my company partner, Billfinger, who were visiting the site and who did collaborate with us to develop that instrument for IMP measurements with Billfinger company. Okay, so I think I should speed up a little bit. I don't know. 5 minutes? 5 minutes? Yeah, okay. So just one more example from the Sonnenblick Observatory with both this insect method and the Pine method. So this is now a bit more information about the station I already mentioned for this dust cloud analysis from the Sahara. So it's a Geosphere Austria station led by Elke Ludewig. And here you see the altitude location. It's really at the summit, at the peak, and the tourist house is just underneath. It's not like in Jungfraujoch or in Schneefernerhaus, or Zugspitze, so it's a mountain station in Germany, where the tourists have the top kind of location and the research station is below. But here the research station is really at the summit and the tourist location is a bit underneath. So it really receives also air from the free troposphere. And you see that in the long-term measurements we did there with, this is now an example of IMP measurements with this offline analysis method over 3 years, together with radon measurement and aerosol measurement. And you see the annual cycles here, which is caused by the fact that in winter we are more frequently receiving free tropospheric air with low aerosol concentrations, low radon concentrations, and low IMP concentrations. And only in summer we see more regional impact of aerosol dispersion and aerosol emissions, so to say, to the station, in particular during sunny days. And also, I don't have the time to show all the details. There's a PhD and a paper is in preparation. We did already see distinct diurnal variability of IMPs during the winter time, where we had flat concentrations all over the day. And only in summer, we did see a diurnal increase of IMP concentrations during the day by convective mixing of boundary layer air into the free troposphere at the site of measurement. So it's very tricky to really know whether you are in the free troposphere or not, but it's very important to measure there, because we need these new measurements of IMPs in the free troposphere, because there's almost nothing measured yet, and it's so important for the CO2 formation processes. For 1 year, we also operated the Pine instrument at the same site. So those are just IMP concentration records over those 3 years, and the 1 year of Pine at different temperatures. That's why the Pine data is a bit higher here, because it's measured at lower temperature. And if you look closer to the Pine time series, you see also then these kind of huge variability and the impact of Saharan dust events. So these, for instance, and this and that, those are clear Saharan dust influence events where the IMP concentration is just peaking in very short time to very high values. Okay, and now just finally, the last example is just, it's called portable Ice-Nucleation experiment, and we use it already in many sites, mostly in the Northern Hemisphere. And here you see some photographs of its transport situations into the high Arctic or with cable cars to mountain stations. This is, that was actually during the pandemic when we operated a US instrument, already in 2020 or 21, I don't recall which year it was. We had a short window of traveling within Europe. So one of my team, Larissa Lacher, went to the INA, the Eastern North Atlantic DOE site, arm site in the Azores Islands, because the US colleagues were not able to travel to the site. So we were able to travel there and operate the instrument for a while. Or here, this is just a transport. I don't know, we had helicopter transport to the Mount Jungfraujoch and many different things. So, and this is just an overview of the different locations we were operating that instrument for IMP measurements over a significant amount of time, at least several weeks long, or sometimes more than or up to a year. And yeah, those are different locations in different kind of seasons, so to say. And here, I think I skip examples of time series. So we get very nice also variability measured. Here, for instance, this is a site in the Schwabenalb in Germany, a low mountain range, so to say, where there's a huge diurnal variability. So those are diurnal cycles. So this is orders of magnitude change between nighttime and daytime of IMP concentrations. I didn't expect that. So with this instrument, we can clearly see that and resolve those diurnal variability at different temperatures. And this is just another example in a rural site in Central Europe, in the Czech Republic. And the quality of data is as such in all the sites we did do the measurements. I just show as a final result an average concentration spectrum of IMP as function of temperature for these different locations. And here you can see how it differs. So this is the temperature range for -20 to -30 in this case. And you see in these rural environments, for instance, in Schwabenalb or in Central Europe, we have high IMP concentrations. And in the more marine influenced areas or in the Arctic areas, we have, of course, less. But also there frequently, sometimes we see remarkably high or large increase of IMPs. So it's not just look at the average. I cannot show more today, but there is more information in the data also for short-term variability, which is really surprising to see that also in such environments like in high Arctic, we see long-range transport impacts of aerosol and also IMP going up within a day or so by orders of magnitude in number concentration. And with this instrument, we can really do that and look into these details. Okay, so as I said, we are developing this aircraft-based version. We had some measurements in the free troposphere already with it on the mountain station. And I think my major interest for the next years in more development and more activities with this instrument is to bring it more to mountain stations. That's why I'm so much interested also to see the mountain station here and others to have the opportunity to sample free tropospheric air, because we have so little measurements in the free troposphere of IMPs, and it's really important to do more in this direction. And mountain stations are one opportunity for that, at least those being in the free troposphere for part of the time over the year, or doing aircraft studies. And that's what we now do with this. This is the aircraft version of the Halo, of the Pine for the Halo aircraft. And this is my co-worker doing that. She did her PhD with developing this instrument, is now preparing for a flight mission with Halo to New Zealand in September. So I hope, my fingers crossed, that we get first good measurements on the research airplane with this version of the Pine instrument, hopefully soon. So this is the next step of improvement, so to say. And with that, I think I can skip that one. It's just targeting the line of developments we do. At the moment, we are building a new lab facility for aerosol cloud climate research. So that will open up in 2 years also for young researchers to collaborate with us. I can only invite everyone being interested to collaborate with us in our labs for also climate research, making use of our facilities together with us in the next years. So this is a brand new cloud simulation chamber, which replaces the one we had the last 25 years. And we certainly will do more with all these point developments. And this is the facility we are using for this topical center for cloud in situ within the Actris framework. So we have several developments ongoing at the moment. And with that, I think I can leave with the summary. I do not need to go through that again. And I'm happy to receive your questions. I hope I could give you a little bit of an insight to our work, at least in Karlsruhe. Okay.
Ok, es momento de preguntas. Creo que allí Michelle levantó la
Next,
mano.
we'll have a Q&A. I don't know if, was it Michelle that raised her hand?
Hello. Thank you very much for a very
Muy-
interesting talk. We always learn a lot when we listen to these talks. I have a question. When you're running an experiment in one of the chambers, you're lowering the pressure, the mixture is cooling, and this crystal starts to form. I noticed that you have a wide range of sizes of these crystals.
Yep.
This has to do that you also have a wide range of sizes in the original particles, or is there another reason?
If you refer to what we measure, the size we measure with the particle counter, so this is not really the geometric size, that was the optical size. And this is kind of a system which is getting an enhanced scattering in sideward direction from the scattering phase function of ice crystals. So they are oversized. And their optical size depends also on their orientation and the crystalline habits. So this is not really the true spectrum of sizes, but you're right, we have a wider spectrum of ice crystal sizes. And we did experiments also to measure that with colleagues bringing instruments like PMS probes from DMT or SPEC Inc. to sample in a vertical line, and then also to measure the crystallographic properties of the ice crystal particles actually. But yeah, measuring their actual size is not so easy. You need an imaging system and you need a good sampling instrument underneath. Yeah. But when they are growing to more than 70 micrometer in geometric diameter, they start falling out very quickly, even in our big chamber. So this is about the limit of sizes we can hold for a minute or so in the chamber. Everything that goes larger than that falls out within 1 or 2 minutes through the chamber to the floor.
Just in that direction, if they start to fall, you also look at some optical patterns like the pillars that we often see in the atmosphere. With
yeah,
optical.
You mean the crystalline habits as a function of the temperature?
No,
or?
that when they fall, they orient in a specific way. The
Yeah,
crystals, and then they show specific optical phenomena.
I know what you mean, but that could be studied maybe in the future in a new facility, because at the moment, not sure if I should go back to that, but if you remember that yeah, you already see it maybe, yeah. I just go back, but we don't have a room underneath, so the only thing we can do is that we go into the cold room, which really is also cooled down to the same temperature as the chamber itself, and then mount instruments there. This is not so easy, so that's why we are limited in measuring in vertical orientation some ice crystal. We tried, but we failed. But the new facility we are now building, actually, and this is a good question. So we are now, one of the reasons to build a new facility at the same place of a similar type is that it's improved in many ways, but we have a cold room underneath, if you look here. So the old chamber was sitting with its insulating box at the floor of the building. This one is elevated, is sitting on the first floor, and we have a controlled cold room underneath where we can control the temperature independently and mount instruments there, which are connected with vertical lines to the chamber above. And there I hope that we can do more of kind of studies you just said, just let crystals fall down through a connection, a pipe connection or something, maybe have an aspiration flow to bring the crystals quickly down to the lab underneath, and then have some optical detection of that. Even maybe measure growth rates or these kind of growth, kind of shape relationships. And the Heimsfield is always talking so much about and others. So then we can look more into these ice crystalline kind of properties, eventually even with scattering. But you know, we have developed, one of my colleagues has developed to measure the scattering phase function of ice crystals also, and we used it already at the facility. So it's called FIPS, particle habit and phase function instrument. It's developed for aircraft use, but we did also operate it in vertical orientation underneath the chamber, and that is taking video images of the same ice crystal when passing by the optical detection volume, so to say, and at the same time measuring the scattering phase function of the same ice crystal. So you get an image, a stereoscopic image from two directions. You only also know the direction, whether it's a plate or a column or something, which you sometimes cannot distinguish when you only look at the side, so to say, and also scattering phase function. And I really want to do more of these studies with the new facility and this new cold room underneath. Yeah.
Gracias, Michelle. Atrás hay una pregunta, Aaron. Gracias. Pueden hacer la pregunta en español si gustan, no hay ningún problema.
Yes, thank you very much for your talk. I don't know if it's an appropriate question, but what do you think about geoengineering based on your experiments that you have done? What's your opinion?
Yeah, okay. Now this is of course a question we could discuss. We should discuss a bit longer, but we are faced with this kind of geoengineering activities anyway. We also had done some experiments in the facility actually. So this is more led by our director, Professor Thomas Leisner. So he had a collaborative project in Germany also with some others taking care of all these kind of related problems. Yeah. And that was on cirrus cloud thinning. Yeah, so this idea to change cirrus clouds and their radiative impact to the climate. Yeah, so the experiments did go very well, but I think many ideas which are out, also using maybe some diamond dust particles from people from MIT or some other ideas. It's nice to think about that, and modeling showed that it might be feasible to do that, but to understand the side effects and the processes related to that, that's the challenge and the need, I would say. And that's why we are open to collaborate with people having ideas about climate engineering, but we would not promote it from our own side on the operational side, but we are open to collaborate to improve the basics that are needed to understand better, not only the impacts, but also the side effects of these things. I hope this is good enough question for you.
Thank you. So we have one question from those online. So thank you very much for the presentation. I have a question. Has any change been observed in the number of ice-nucleating particles in the global atmosphere as a result of climate change?
Oh, this is a difficult question. Maybe I'm not the right person to answer that. The question was whether there's already an observable change of number of ice crystals according to climate change. Yeah. Good question.
But I think that there we will need maybe longer time series, because you show us very nice time series, but they're very short to answer this type of questions, right? So we'll need maybe 20, 30 years.
Maybe I can sneak away a little bit from the core question. I think what I understand, I'm not so much in these kind of intensive field observations with aircraft, so these kind of cloud studies and everything. If you just do these kind of intensive observations, as you said, they are just looking into one cloud at one season in one location. And we are missing these longer term records. Maybe from satellites it's better, but I'm also not so much aware about satellite results for ice number considerations. Yeah, I think liquid water content and an ice water path and all that, maybe that's better constrained from satellite observations. But we are really missing longer term reliable and accurate in situ observations, at least, I would say. And this is one of the interests of this ACTRIS network, is exactly in that direction. And we have this cloud in situ kind of topical center, as we call it, which is not only looking at ice-nucleating particles, so we also collaborate with other partners in Europe to really measure in mountain stations, in clouds in the future, hopefully also the size distribution of droplets, not only the liquid water content, also the size distribution, and also the ice content, if possible, wherever possible in a mountain. It's not so easy to measure ice in clouds anyway. Yeah? But we need these longer term monitoring observations with instrumentation which are validated and quality assured and approved. And this is, I think, what we are missing at least. And I cannot comment on the satellite observation, whether they can already do that. But for in situ measurements, I think we need these longer term measurement observations.
Okay, thank you. Is there any other question? Well, maybe I have one because, most of the available IMP measurements that we have globally, they have been done at the ground level,
Yeah.
and you show us a figure that the concentration of particles within the free troposphere and the boundary layer, they are quite different. So is it a true assumption that what we measure at the ground level is what is happening up in the atmosphere or within the clouds?
Yeah, there's many questions also and debates about how relevant the measurements at the ground are for cloud-based processes or cloud internal processes. I think as long as we are in a well-mixed boundary layer, we may be on the fair side, but there may be other environments where this is not the case. Actually, one of my students, the one that graduated last Friday, I did not show results from him, but he measured with UAVs. So we were developing a sampling system for UAV, and he was flying that together with colleagues from FMI in Finland, in the Arctic, in northern Finland area. And he sampled aerosol at the ground and 100 meters above. And already there he did see different concentrations. That was in autumn when these kind of Arctic layer clouds, stratocumulus clouds start to form. We don't know yet why that was the case, but we did see more above than below. So obviously there was long-range transport from higher layers, downward mixing eventually. This is also a question, are these kind of layer clouds fed by IMPs from below or from above even? Right. So it's not so clear. And this, it was only 8 cases, 8 UAV flights he was able to do as part of his PhD as a pilot study. In 6 or in 8 out of 10 cases, I think, or 6 out of 8, we did see clearly more IMPs 100 meters above surface than at the surface. That was intriguing and interesting. So we definitely need to do more of these vertical sounding, and maybe tethered balloon setups may be appropriate, UAV may be appropriate, but certainly not aviation, jet aviation aircraft studies. They're too expensive, but maybe these new developments with lightweight sensors, lightweight systems, UAV developments, it may be better suited to learn more about vertical distribution also of IMPs. But I have the feeling that what you may expect in terms of a variability of IMP concentration with height may be less than the sensitivity of cloud, so to say. So maybe the sensitivity of the cloud to a certain level of IMPs may be more important to know than the change of concentrations from the surface to the cloud layer. And also, don't know what happens inside the cloud. Does a cloud reduce IMPs or does it enrich IMPs? We have no measurements of IMPs inside clouds almost. That is also needed, I think, because a cloud is a dynamic system. It's not that it forms and it disappears again. So there's air flowing through a cloud. Air is coming from above, from the side. There's mixing processes going on. There's also indication. I think that there may even be more. So they may kind of accumulate particles even rather than, if they are not precipitating, rather than reducing or diminishing. So all those things are almost unknown. But we need to know that.
Okay, thank you. ¿Alguna otra pregunta? Hay una aquí.
Hi, Ottmar. Thank you so much for your talk. My question is about the other processes. I don't know, like secondary processors or something like that.
Mm-hmm.
It is possible to measure this type of processes in
the chamber, it's not so easy. We tried here and there, but you need collisions for that, and so the number of collisions at the concentrations we do our experiments are not so fast or so much in a certain amount of time we can control the cloud. But in another lab, in a smaller lab in our institute, led by Thomas Leiser and Alex Kiselev, so they are studying secondary ice in levitated droplets and ice crystals. So they know more about that, and they're definitely important in many cloud types, of course, but maybe not in all of them.
Yeah, thank you so much. Maybe it can be related with the talk.
But in the chamber, it's difficult to control. Maybe we find ways.
Okay.
Younger people, more smart people find ways of doing experiments like that. We would be prepared of doing that, but so far we didn't go into that so much. So someone needs to develop good ideas, so to say. It's not impossible, but difficult.
Yeah, thank you.
Gracias, Sebastián. ¿Alguna otra pregunta?
Thank you,
Maybe I have
Sebastian.
a follow-up, because most of the climate models,
La
they
mayor parte,
use again
la,
parametrizations that were obtained from ground-based measurements. So is that why you said that we have to go to the free troposphere to get perhaps a more, more accurate data sets in order to improve the currently available parametrizations, in order that the delivery data, the data that we get from the models is more accurate?
Yeah, many of the climate models, as far as I understand, do not even use aerosol-specific parameterizations for heterogeneous ice formation. Maybe for homogeneous freezing, it's more elaborated with these freezing rate equations for homogeneous freezing. But the big question is whether cirrus cloud forms more by IMP processes or by homogeneous freezing. This was not a topic here, but the question is how often do we reach these high supersaturation levels where homogeneous freezing can kick in? And that very much depends not only on the dynamics, the cooling rates and the waves and all that in the free troposphere, but also on the number concentration of IMPs that contribute to cirrus ice formation already at lower supersaturations, and is then reducing or removing the water vapor out of the atmosphere while the system still evolves, or the cloud evolves, or expansion continues and things like that. So that is very important, and there's almost no direct measurement available. And there's some modeling, like there's one modeling study from the DLR group that predicts remarkably high IMP concentrations based on the lab studies and what they know about aerosol dispersion in the free troposphere. So it's the abundance of aerosol types and the number concentration in the free troposphere is reasonably well described in some models. But when you then apply the lab-based parameterizations to that and calculate how many IPs should be there, it's really high numbers. Maybe more than some models assume for this kind of dynamic process for heterogeneous and homogeneous freezing in cirrus formation. So I think there is a kind of a discrepancy and a need for better measurements to really constrain the models with what is measured as IMP concentrations, in my mind.
Thank you very much. So is there any very final question? If not, so we would like to thank Ottmar for his great presentation. So we have this little certificate. Thank you very much.
Thank you so much.
And our institute also have a little gift for you. So thank you very much for coming.
Thank you. Thank you so much for inviting.
Thank you.
And for. Thanks.